The videos today are about the topic of object localization within the broader topic of machine vision. In the previous videos, we've learned a method that is similar to a center of mass calculation to find the X and Y location of an object in units of pixels. Knowing the location of an object in units of pixels is only useful to us as long as we're using the information within the image. As soon as we decide that we want to use the information about the location of the object outside the image, for example in a pick and place operation, it's much more useful to us to know the location of the object in physical units like inches or millimeters or feet or meters. So what kind of a conversion can we use to convert the XY location of an object in pixels to an XY location in meters? This is the process that we're going to be learning in these videos. The process is a little bit complex and requires a couple of steps. Fortunately, we've already learned some of these steps previously when we were learning about kinematics, so some of these concepts will seem familiar to you. Let's take a look at how this conversion can be done. To begin with, let's make sure we understand what the problem is that we're trying to solve. Suppose that we have captured an image with our camera, and the image is in a rectangle as I'm showing drawn here. This image has dimensions in pixels. For example, a common dimension in pixels for an image would be 640 pixels in the horizontal direction and 480 pixels in the vertical direction. So these numbers are both in units of pixels. The output of the center of mass calculation is in units of pixels. Many times the zero location of an image is in the upper left hand corner, as I'm showing drawn here. This dot represents the location 0, 0 in our image. After we've done the center of mass calculation, we might find out that the object is located, for example, 240 pixels from the left and maybe 120 pixels from the top. Now, let's suppose that this image is looking down at the workspace of my robot manipulator. I'm going to draw a top-down view of a manipulator here to illustrate what I'm talking about. Here I've drawn a 3 degree of freedom articulated manipulator from the top view. If you remember from our unit on kinematics, this manipulator has its own base frame, that is, a frame that's attached to the ground that we use to do our kinematics and coordinate transformations. We've already learned how to find the location of the end effector relative to the base frame. We've also learned how to find the location of an object in pixel units within the field of view of our camera. Now we want to combine these two things. I would like to find the location of the object not in units of pixels, but in units of meters or inches or centimeters or something like that in the base frame, that is, in my manipulator's base frame. So how can I do that? Let's take a look at the process of how we go from the location of an object in units of pixels in the field of view of the camera into physical distance units in the base frame of the manipulator. There are 6 steps involved in transforming a point in the camera frame into a point in the physical base frame of the manipulator. Step 1 is to convert our pixel units into physical units. We do this by using what we know about the field of view of the camera. For example, if we know that the resolution of the camera in the horizontal direction is 640 pixels, And we know that the field of view of the camera in the horizontal direction is, let's say, 2 meters. This gives us a conversion factor between pixels and meters. We have a conversion factor here of 2 meters per 640 pixels, or in other words, 1 divided by 320 meters per pixel. Now, when we multiply this value by the pixel location of the object, it will give us the location of the object in meters. Back in our example, I said that I knew the location of the object as 240 pixels in the horizontal direction. So I'm going to now go convert that into physical units. So that the meter, or physical location of the object, is 0.5 meters in the horizontal direction. I could do the same thing to find the vertical location of the object, and I'll do that real quickly here. We said that the vertical location of the object in pixel units is 120 pixels. I'll use my pixel to meter conversion factor. To find the vertical location of the object. And we're now done with step 1, which was to convert pixel units to physical units. Step 2 is to draw the camera frame, and we'll call that frame C. Let's go back to our drawing of the image, and we need to draw in the camera frame. Now, since 0, 0 is typically in the upper left-hand corner, I want to draw my camera frame with its origin there in the upper left-hand corner. I also want to make sure and draw this frame so that it's a right-hand frame, and I'd like Z to be coming out of the page. So, because of that, I'm going to draw the X frame for the camera going down, and I'll draw the Y frame of the camera going off to the right. That will give me a right-hand coordinate system with Z coming out of the page. And now I'm done with step 2. Step 3 is to find the rotation from the camera frame to the base frame. Essentially, the process that we're following here is a coordinate transformation. We know the location of a point in the camera frame, but we want to find the location of the point in the base frame of our manipulator. So in order to do that, we're going to use the same process that we've used for coordinate transformations in the past. We're going to start by finding the homogeneous transformation matrix from the camera frame to the base frame of the manipulator. That's why we're in step 3 finding the rotation from the camera frame to the base frame. Our homogeneous transformation matrix needs a rotation and also a displacement. Let's go find the rotation from the camera frame to the base frame. To help me find the rotation from the camera frame to the base frame, I'm going to draw in dashed lines, the camera frame right on top of the base frame. The rotation angle between these two frames from the camera frame to the base frame is this rotation angle right there. And that's a rotation around the Z-axis, because remember that my Z-axis in the camera frame is coming out of the page. Because the rotation is an angle of theta around the Z-axis, I can easily find the rotation matrix by pulling out the standard form of the rotation matrix around the Z-axis and plugging in the angle theta. We can write that like this. The rotation from the camera frame to the base frame 0 is equal to a standard rotation matrix around Z with the angle theta plugged in. We're now done with step 3. You might be able to anticipate what step 4 is in this process. Since we need to find a homogeneous transformation matrix, and we've already found the rotation, the next step is to find the displacement between the center of the camera frame and the center of the base frame. Let's go do that now. In practice, it often helps to find the location of the center of the base frame by placing an object at the center of the base frame and using our image processing knowledge to find the location of that object. In this case, I'm just going to tell you what the displacement is. Let's suppose that the center of the base frame is directly in the center of the image, so that the vertical displacement is 240 pixels and the horizontal displacement is 320 pixels. We can now take those numbers and convert them to physical units using the same pixel conversion factor 1/320 that we found previously. Since we called the horizontal direction y and the vertical direction x, we need to use that knowledge here when we find the displacement. The x displacement from C to frame 0 will be 240 pixels converted to the physical units. Let's also find the y displacement. The y displacement here is 320 pixels. Now that we have the displacement from frame C, the camera frame, to frame 0, and we have the rotation from frame C to frame 0, step number 5 is to make the homogeneous transformation matrix. Since this is the homogeneous transformation matrix from the camera frame to frame 0, we plug in the rotation that we got from C to 0, we add on the displacement, and then we end the matrix with a row of zeros and a 1. We now have the homogeneous transformation matrix that we can use to convert points between camera frame and the base frame of our manipulator. Step 6 is to use this homogeneous transformation matrix in a coordinate transformation. Remember that the coordinate transformation works like this. A point in the camera frame is equal to the homogeneous transformation matrix from the camera frame to the base frame times a point in the base frame. Now, in this case, we actually want to do this transformation the other way. I know the location of a point in the camera frame, and I want to get the location of the point in the base frame. So we can do this simply by finding the inverse of the homogeneous transformation matrix. In other words, this other equation also holds. A point in the base frame is equal to the inverse of the homogeneous transformation matrix from camera to 0 times a point in the camera frame. We already found the location of a point in the camera frame. We did that back in step 1. In step 1, we converted the pixel units of the object we want to find the location of to physical units. And what we came up with is the location of a point, horizontal and vertical, that we want to transform from the camera frame to the base frame. So let's make sure that we know which of these numbers is x and which is y. If we look back at our picture, we see that we made the horizontal direction in the camera frame be y and the vertical direction be x. So here, the horizontal number is our y value and the vertical number is our x value. So the point in the camera frame starts with the x value. The x value is the vertical value, so we'll fill in 0.375. Next comes the y value. The y value was the horizontal value, which we calculated to be 0.75. The z displacement is 0 because all of the points are on the ground. Finally, to find the value of a point, in order to use it in a coordinate transformation, we always have to stick a 1 down at the end so that the matrix multiplication will work. We can now take this point in the camera frame, multiply it by the inverse of the homogeneous transformation matrix that we found, and find the location of that point in the base frame.